Okay, I was actually getting distracted. I was still talking about branching, and then we went all off on the tangent of why there's liquid in the tin. Okay, but it had to do with the fact that if the bigger the distance is between two molecules, the weaker the force would be to attract them together. Does that make sense? Now, the reason then why branches are have an effect on the molecular force is that if I have a branch, if I have a molecule with a branch and another molecule with a branch, do you notice that the branches hinder the two molecules to get close to each other? Hinders. The branch hinders the molecule getting right up to the other molecule. It creates separation between the molecules. It's something that, so for example, if I had a bunch of pipes, I can stack the pipes quite nicely together, and so the pipes can actually, with their whole length, touch each other. Okay? You guys understand what I mean if I say that? But if I had a branch, or a branch with branches, and I had another branch with branches, the branches actually avoid or makes it more difficult for me. So let's say these were logs, that's maybe a better example. Branches make it difficult for the two branches to be lying straight next to each other. Okay. So that because there's a hindrance between the two branches coming close, the force that they can exist on one another is smaller. So the more branches I have, the more hindrances there are. Does that make sense? The more difficult it is for two molecules to get close together. So what effect does branches have on intermolecular force? It lowers the intermolecular force. Why? Because it increases the distance between the molecules. You increase the distance between molecules, the forces that exist between those molecules are smaller, and as a result, the kinetic energy needed to escape is less. So I boil at a lower temperature. Okay, does that make sense? Now, just to talk a little bit and about the other properties. I've just been looking at boiling point because it's just a good and easy to understand concept when it comes to the energy that's needed. But what we also get is viscosity. Who knows what's viscosity? Who knows how to spell it? Because I don't. Okay, you know what I'm talking about. What is viscosity?
It's the ability for molecules to flow, isn't it?
Okay, it's the opposite of that. It's the resistance of molecules to flow. So, in other words, when you have a substance that if you were to throw it against the wall, it would flow down very slowly. Okay, it's very viscous. It means it resists flow. Now, what do you think? Will strong molecular forces increase or decrease viscosity? It will. So stronger viscosity will, stronger forces will decrease viscosity.
No, solids will, because viscosity is the resistance, right? So it will increase the viscosity.
Yes. So if I've got strong forces, the molecules are holding on to one another, and so it doesn't want to flow. Does that make sense?
Yes.
So stronger forces leads stronger viscosity, more resistance to flow. Okay, so viscosity, the resistance to flow. So let's think of something that is viscous, like syrup and water. Which one between syrup and water has the more resistance to flow? Syrup. Now syrup is sugar mixed with water and melted together. Okay, sugar is C12H12. H22O. Water is H2O. Okay. What is causing sugar's viscosity? So sugar melted in water now, it's now in a liquid form. Okay. But can you see what causes the viscosity? Well, sugar, I suppose, is a solid. But just as an example now, can you see what causes the viscosity? Which one between these two will have the strongest forces? What forces will we have here?
Hydrogen and dipole. No,
Right.
hydrogen. No, sorry.
Hydrogen bond forces and induced dipole. Why induced dipole? Sorry? What was induced dipole, guys?
Isn't it the highest was electronegativity?
Please speak louder, Connie. I can really not hear you.
It has the highest electronegativity.
No, that was dipole.
No, I mean it has the highest.
Isn't it when they have more
Oh,
space?
when it's induced, it has the.
Induced is when the molecule is big. Surface area. Okay, increased surface area causes induced dipole forces, London forces, and it comes from that long carbon chain. So this one has induced dipole forces and a hydrogen bonds. While this one, only water, is just hydrogen bonds. You understand? Okay, so that is why they resist flow so much, and why if you want to put syrup on your bread, you have to shake that bottle. Well, if you wanted to put water on your bread, it'll just flow it out, isn't it? Okay, so that's viscosity. The next one is vapor pressure. Vapor pressure got me confused for a long time. Okay, but it's almost as simple as just thinking of smell. Okay, you smell things because the molecules of that thing has reached your nose. Does that make sense? Okay, you can't smell the table, okay, because it's not releasing molecules in the air. Okay? So vapor is literally when on the surface of your liquid, so you've got a liquid, the molecules on the surface only has the molecules right below them keeping them there. Okay, so there's fewer molecules keeping them in. And so they might have enough energy to escape, causing vapor. Does that make sense? Now, the stronger the forces, will that increase ability to escape or decrease ability to escape?
Decrease.
It will decrease, because if I am stronger to keep you here, you can't escape. Now vapor pressure has got to do with, let's say we were to close that this in a container, it will still cause vapor, and because it causes vapor, the gas part takes up more space than the liquid part. So when it escapes, it causes pressure in that container. Do you understand? Because it's now taking up more space than it did when it was still liquid. Makes sense? So that's causing pressure. So for example, if there was a little membrane here, like a piece of balloon, like just something that can stretch, it will, after a while, it will just start blowing up a little bit. Do you understand what I mean? If I say pressure, a balloon blows up because you're putting pressure inside. Okay. So vapor pressure will increase if there's a decrease in intermolecular forces. Does that make sense? Because if the forces that keeps them together is less, then the molecules at the surface will escape easier. Okay. So this is a common question in esters. They will ask, why do longer chain lengths of ester esters have these very nice or distinct smells? Why do longer chain length esters have weaker smells? And it's because a longer chain length means more induced dipole forces, stronger induced dipole forces, which keeps molecules together so that they do not escape, thereby reducing the vapor pressure. Does that make sense? So an ester with very few carbons will have a very strong, distinct smell. And look at that. So look at the shortest esters and what they smell like. They're strong, fragrant smells. For example, methyl acetate smells like glue. It is that very strong smell. That's a short one. Another short one. The longer ones will probably, they won't be so able to smell them. Let's find another short one. There's a shortish one. Okay, smelling like lemon or rum. Okay. Another short one was where was it? I saw it just now. Ethyl acetate, there we go. Ethyl acetate smells like nail polish remover. Okay, or again airplane glue. Very distinct smells. You will smell it from far off already. Okay, so let's look at a few exam questions. Okay, this was an exam question from this current exam, the last one we wrote. Consider the table below. We've got the homologous series. Bad pronounce. Okay, the alkane. So just this little table, we'll look at that just now. And then we've got questions based on that. Now this is a very common way of asking organic chemistry. So let's go through these questions. The first one, give the name and molecular formula for the example at A. So there's an alkane. There's an example of the alkane, the name, and then they give us the structural group. In other words, just the functional group of the structure of the functional group. And we know alkanes have that single bond between two carbons. Alkenes a double bond. This one has a double bonded carbon, a single bonded oxygen, but that oxygen is bonded to a hydrogen. So these will be carbons. So it's carbon bonded to oxygen, double bonded to hydroxy is carboxylic acid. So this is carboxylic acid, and then this one they didn't show us, but it's methanol. Methanol is a what type? Aldehyde. It is a carbon,
oxygen, and alkyl. That A-L-K-Y, alkyl, and a hydrogen.
Well done. So it's a carbon double bonded to an oxygen, like here, but single bonded with, like this one, just without the oxygen there. Okay, that's single bonded too. Okay, so give the name and molecular formula for the compound example at A. So this A, how will we know? We know it's an alkane, but it's this alkane because here's the condensed structural formula for the example. So what is the name? Notice we've got 1, 2, 3, 4, 5. 5 is no branches. A branch would have been in brackets, but there's no branches. 5, what will that be? Pentane. So this is pentane. And then the molecular formula. Molecular formula means every molecule and how many of them there are. So there's
5 H12.
Pentanes or alkanes will always have 2 more than double. So the general formula will be CnH2n plus 2. 2 more than double. Okay. Give an example of an alkane used in everyday. So there you could have For example, in lighter gas, we use ethane, but you could have put lighter gas. Octane is used in petrol. You could have even said, I don't know what it's called, but a candle is also an example of an alkane that's used in everyday life. Okay. Give the condensed structural formula for B and D. Okay. So condensed structural formula at B and D, this is now this structure. So we have 2-methyl-pentene. So after my second carbon, I must have a methyl, which is a branch. So I have one carbon. My first carbon will always, well, it now depends. Let's first just draw it. I like to draw it rather. I've got a pentene, so I've got 1, 2, 3, 4, 5. On my first one, I've got a double bond, and then on my second one, I've got a methyl, which is a CH3. So this one here has 2 left, so he's got 2 hydrogens. This one here has none left, no valence electrons left. This one here has 2 left, so I've got 2 hydrogens. This one here has 2 left, so 2 hydrogens. And this one here has 3 left, so 3 hydrogens. The ones on the ends, I always have 3 unless it has a double or triple bond. So this one will be CH2, and then C is no H's, just my branch, CH3. There's only one branch. If there was another branch, I would have put a 2 there. Then CH2, CH2, CH3. Okay.
It's good to draw.
Yeah, I always draw it first. I can't do it in my head. Okay, then at D, we have butanoic acid. So I know I have the ester, so I start with that. Okay, there's my ester aspect. Now there must be not an ester. Sorry, I know I have my oic acid. Okay, that's my oic acid. You'll see oic acids always end on COOH, COO. Okay, they always end on COO. So I know I'm going to end with that. Butan just means there's 4. So there's 4. There's my 4, 1, 2, 3, 4. And then this one has 1, 2, 3, 4. He's happy. This one needs 2 hydrogens. This one needs 2 hydrogens. This one needs 3. So CH3, CH2, CH2, COO. Okay.
Cool.
Then name the homologous series at C and E. So, butanoic acid forms part of the carboxylic acids, and methanol is an aldehyde. Okay, so how I would remember is al, it ends on al, and it's aldehyde. Okay, so it's not difficult. And obviously any oic acid is the carboxylic acid. Okay, so that's just not difficult. Draw the functional group to which F belongs. So that's what we were talking about earlier. The functional group here, we know that it's either a hydrocarbon, which is alkene, alkynes, and alkanes, alkenes, and alkynes, or it's a halogen, which means carbon and halogen, haloalkane, or it is a alcohol, which is carbon and hydroxyl, or all of the rest that we have is carbon double bonded to oxygen. And it's all about what happens now on here. And with aldehyde, methanol would have one of them must be a hydrogen. Okay, so the functional group, you shouldn't have drawn anything there. If you did, you should have only put an R. it's representing that that's just a substituent or an alkyl group. Okay. Define the term isomer. What's an isomer?
Things belonging to the same.
Has everyone got this right?
The same what? I think the same group, the same molecular formula.
It's got the same molecular formula,
A different structure.
different structure. So in other words, we use the same molecules. We use the same molecules to create the the two structures have the same molecules in them, but they look different. They've got different structures, and it's not like the one has the hydroxyl at the front and the other one has it at the back, because that's just looking at it from a different perspective. Okay. For example, if it was something like that, I could maybe have the hydroxy at the end, or I could have the hydroxy in the middle. But there's only two. It's either at the end or in the middle. Those would be two isomers. They've got the same molecules, but a different structure. Okay. Here they say, refer to the 2D in the table. Draw a structural formula for an isomer of this compound. So here's D. Okay, butanoic acid. Let's just draw butanoic acid to begin with. We already did, isn't it? Now for an isomer. Okay, all I need to do is break up anything at the end and plug it in somewhere else. That's what I did here. I just broke it off here and plugged it in there. Okay, so what I could do is I could take this carbon, and I could just say, okay, this is CH. Instead of being at the end, I could just put it on the second last one. So I could have just drawn it like this. So here's my structure with the end broken off. Okay, and now I have an option. Where can I put it? Now, just take away all the H's and you'll plug in the H's later. Okay, so I could put it, if I put it here, I just have the original one again. Okay, so I won't put it there, I'll put it there, CH3, so I took out the CH3, and now this one needs an H3. This one has now 1, 2, 3, needs one H, and this one doesn't get anything. Okay? Alternatively, I could have taken away this H on this side. And so I had CH3, CH, no, just C. I think I could have done that. Let's see. Double bond, oxygen, single bond, oxygen. Now instead of that
they
H.
always go together, don't they?
Sorry?
You're saying the OH always has to be next to each other.
No, because you're doing an isomer. An isomer has a different structure, so you can break it up for this. But we must just see that we have the same amount of.
I see.
So what happened to this H is this one is now CH3, CH2. You see, in this one, that one only had one. That hydrogen that's there now came and joined on this one, CH2. So this one still has nothing. So here, yeah, I could have done that, you see. I could have also taken this, broken off another one and taken it there. Okay, so in other words, here's another option, CH3, C, CH2, CH3. Sorry, I'm missing an oxygen. One oxygen and then that CH2, CH3. So I just moved it from this side to that side. What did I create here? this one is it's a carboxylic acid with a branch. So this one will be methyl. The next one is, they ask for the name. So this one is methyl. And then 1, 2, 3, propanoic acid. And I must just say that this is on the, well, I don't have to say it, but I could say 2-methylpropanoic acid. Okay? This one, what did I create here? Ester. So this is an ester. And the ester, the carbon that's connected to both is the one that's in the main branch. Always. So this is the main branch. Even though here there's two the same length branches, the carbon connected to the both is the main branch. So this is CH, and I say that because we could have had another one like this, where this is just an H. Oh, and now I took this one that side as well, CH2, CH2, CH3. Okay, could have done that as well. So in other words, the 3 H's there was lost, 2 of them, 1 left, and the carbon, and they just came to this side to make another CH2. See that? Okay, so that one always forms the main branch. That's the 1, 2, 3. That's the propanoate. And then there's the methyl branch. Methyl propanoate. This one has 2, so that is ethanoate. Ethanoate. And then he has an ethyl branch, so it's ethyl, ethanoate. This one has a single carbon in the main branch, so this is methanoate. And then he's got 3 in his branch, which is propyl. Okay? That's fine. The next question there was, name the homologous series to which this isomer belonged to. So for our first one, it was carboxylic acid. And if you had any of the others as an answer, it would have been esters. Okay, let me just get to the next exam question, then I'll get back to that question. The next exam question was methylpropanol and butanol are 2 organic compounds with different properties, yet they have the same molecular formula. So, methylpropanol, propanol means it's carbon double bonded to oxygen, single bonded to hydrogen. That's what make it an aldehyde, hide. And then propanol means there's 3 carbons. Okay, methyl means there's a branch on the first carbon because it's not written, but I can't put a branch here. Then it wouldn't be methylpropanol, it would be butanol. So you can't have a branch on the first one, it must be on the second one. Okay, so there's methylpropanol, and then butanol is exactly 1, 2, 3 carbons, 4 carbons, sorry, with the H. So they've got the same molecular formula because both of them is CH4. Then each carbon has 2 hydrogens, okay, except for, so there's 2 hydrogens per carbon, so each carbon has 2 hydrogens, except for the first one has 3, so there's 2, 4, 5, 6, 7, 8 carbons, hydrogens, and 1 oxygen. Okay, that was important because what is the molecular formula and molecular mass of these 2 compounds? Everyone went and calculated both for me. If you have the same molecular formula, you have the same molecular mass. In other words, they've got the same molecular formula. So they must have the same molecular mass. So there's the molecular formula. Molecular mass is carbon has a mass of 12. So 12 times 4. Hydrogen has a mass of 1. So it's 1 times 8. And then oxygen has a mass of 16. And there's just one of them. 12 times 4 is 48, plus 8 is 56, plus 16 is 72. Okay. What type of intermolecular force is found in aldehydes? Well done. Dipole forces.
Also, this is the first they were asking.
Ish.
I didn't know what it.
Hmm?
I didn't know what it was.
This question, I was like, what? I got the first one. 4.1.
Which one of the above mentioned compounds will have the higher boiling point? Give a reason for your answer.
Which a higher boiling point would have to be
Butane.
Why butanol?
Have
I see
the longest structure.
No.
isn't it the
We
other
never
one?
said.
Side.
So
Branch.
again,
The one with the branch.
it's
Branches.
yes, the longest structure has an effect, okay, but it's only because of the size of the molecule, the space. So it doesn't have the longest structure really. Both of them have the same surface area. So that's what we were talking about. The surface area for both of these are exactly the same, even though there's branching. So a lot of people think that if I were to make a branch, I will change the surface area, but no. If I take a piece of clay here and I break a piece off the clay, what have I done to the surface area of the together? Still, the total surface area, if I take them together, is it more or less?
If you break the
So imagine now my arms are 2.
And it's more.
If I break the surface area, now there's more surface area because there's now this part that used to be connected is now
That's
exposed.
right.
But now, this part gets stuck there. So is this still exposed? No. And this little part that used to be exposed is not exposed anymore. So even though this side, you see, so the two sides that's exposed now is again taken away with that. So surface area for these two haven't changed. In other words, the induced dipole forces for these two are the same. You understand what I'm saying? There's still the same amount of space for the molecules for the electrons to move around it. Does that make sense? So the length of the structure is not what it's about. It's about the surface area of the molecule. Okay? That has that effect. Okay, but now, so they have the same surface area because they've got the same molecules. Do you understand? So what did you guys say? So you are right, it is butanol, but what is the correct reason? Why does butanol have a higher boiling point? You guys have it right.
Because
Yeah?
it needs more energy to break the bond between the carbon atoms.
No, you're again going in the wrong direction.
Right.
Why is it taking more energy to break that bond? So yes, it's got a higher boiling point, which means we need more energy to overcome the intermolecular forces. Yes, but why? Why do we need more energy? Because the intermolecular forces is stronger in butanol. But that's the question. Why is the intermolecular forces stronger in butanol than in methyl protanol? You guys said it just now. Guys, I'm so disappointed. Because this one has branches.
But
But so I said branches have nothing to do with it. I said that long time ago.
When did I say branches had nothing to do with it?
Because you see the surface area doesn't change.
But the surface area doesn't change.
Oh, okay.
Branches doesn't change the surface area. That's not why they weaken the force. It's the same surface area. What does branches do? What do branches? No, they hinder the molecules from contact. They reduce the ability of molecules to get close enough to each other. So, butanol's forces are stronger. They've basically got the same induced dipole forces. But butanol's forces are more effective because his molecules can just go next to each other. Like butanol literally looks like this. Literally like that. And here's another butanol, and they just go like that. Sorry, I'm going to go on. So, reason for me now out, or give me the reason why would butanol have a higher boiling point than methyl propanol?
Because it doesn't have a branch.
You're not giving me a reason. You're not giving me reasons. You're giving me a phrase, but you're not getting to the conclusion. You understand what I mean? So you must say,
Can I try?
yes.
I think it's because it takes less energy to break branches.
You're
So
not trying to
that's-
break branches.
But that's what the heat is doing, you understand?
It's not breaking branches. Breaking branches means you're
Okay,
Literally.
wait, it's separating.
to
the
separating
branch from-
molecules
Yes,
with branches.
yes.
That's a better way of saying it. It takes less energy to separate molecules with branches. Why?
Because the intermolecular forces between the branch
Branch
and
molecules.
the main chain are weaker.
It's not between the branch and the main chain. It's between, see, intermolecular forces is not about the branches and the, it's about two molecules. Both have branches. And they're both attracted to one another. So to break that bond takes less energy because the force that exists between those two molecules are weaker. Does that make sense? The force that exists between branched molecules are weaker than the force that exists between unbranched molecules. Because, and then you can go ahead, you don't have to say that, but you can go ahead and say because branches hinder the attraction between molecules. Okay? Or produces distance between the molecules. Great. And so again, it takes less energy, and because it takes less energy, which one will, so remember what they say, which one has the highest boiling point? Why? So you are saying methyl propanol has a lower boiling point. That's why butanol will have a higher boiling point. Okay? Identify the compound which will have a higher vapor pressure.
Wasn't also butanol?
Sorry, isn't it also?
Butanol.
So let's reason it out. What is vapor pressure?
Vapor pressure, isn't it when it's about to melt? Pressure on top.
The
Wait,
process
isn't
happens
it-
when the water evaporates.
It's not water.
Vapor pressure has a low.
It's liquid.
Yes.
You can't say when water evaporates. We're talking about liquid evaporates. When,
So,
yeah.
sorry, isn't it that methyl propanol will have a higher vapor pressure because remember what we said with the branches and the intermolecular forces that exist. Since they are weaker, the molecules on the surface, it will be easier to let them go.
It's exactly it. No, it's perfect. I would just not use to explain it makes sense to say to let them go, but you'll just use the word forces. The forces that exist to keep them there are weaker in methylpropanol than the forces that exist in butanol. Do you understand, Olivia?
Okay.
So vapor pressure is the ability to release vapor. So I release vapor more when my forces are weak.
Okay.
So branched will release more vapors than unbranched. Okay? Identify the compound. Which one between ethanoic acid and butanoic acid will have higher viscosity? What is viscosity?
The resistance to flow.
When will I have higher viscosity?
When we have strong
Good.
intermolecular forces.
Strong forces.
So in this
What's the
case,
difference between those two things?
Between
Between
carbon.
ethanoic and butanoic.
F has 2 and then but
has 4. So that means that the intermolecular forces in ethanoic acid, I'm thinking, are stronger are weaker
Weaker.
than the butanoic acid. So butanoic acid will have a higher viscosity.
Does that make sense? What is the difference between the forces? Which forces is stronger in butanoic acid? Let's start by what forces do we have in butanoic acid?
In butanoic acid, we have induced dipole and
So what is the
dipole.
so this is how you would know. You would always look for an oxygen. If there's an oxygen and it's connected to a hydrogen, you know what forces exist. Hydrogen bond. Hydrogen, not hydrogen forces, hydrogen bond forces. Okay? Does ethanoic acid have that? Butanoic, oic acids, carboxylic acids. Yes, they do.
Hydrogen bonds. OH. Yes.
OH has an OH. Okay. After you look for that, you'll look for the oxygen. After, let's say it has hydrogen, this one has hydrogen bonds. But what it also has is, now look for more oxygens. If it has oxygen bonded to a carbon or to anything else than hydrogen, it will be dipole, dipole. So this one has hydrogen bonds, hydrogen forces, hydrogen bond forces, dipole, dipole forces. But what butanoic acid also has is induced dipole, because it's getting bigger. You getting this?
Yes.
Right, so you start with oxygen. Look for oxygen and hydrogen bonded together, not? So for example, this is C, carbon, oxygen, and hydrogen. This is methanol. Okay, CH 21 CHOH. Yeah, that's methanol. Does it have an OH?
Yes.
No, it doesn't. Methanol looks like this. It's actually, wait, it's actually like this. CH2O. Sorry, I wrote it wrong.
Okay.
It's actually like that. Does it have an OH?
No.
Oxygen bonded. So in other words, OH is oxygen bonded to hydrogen. Yes, it has an O, it has an H, but oxygen is not pulling on hydrogen. It's pulling on carbon. So this one will have dipole, dipole. Okay, so first we look for oxygen. If oxygen and hydrogen are bonded, hydrogen bonds. Then I'll look for oxygen bonded to carbon or anything else. If oxygen is bonded to anything else, it's dipole, dipole. Okay, if there's not dipole, dipole, it means it must be induced dipole. Okay, that's simple enough. Cool. Let's then just do a few more exam questions, similar to what you'll find in the exam. Susan is supplied with 4 bottles containing 4 different organic compounds. She takes a sample from each bottle and determines the boiling point of each under the same conditions. The results are shown below. So she determines the boiling points of these things. These are the boiling points. And now they ask for questions related to this experiment. For this experiment, write down the independent variable. Now, an independent variable is the variable that you can change. Okay? It's the variable you can change. The dependent variable, you cannot change that variable. It depends on the variable that you changed. Does that make sense?
Yes.
Okay. So which one is the independent variable?
It's boiling
How can you change boiling point?
by increasing or decreasing the temperature.
No, you're misunderstanding boiling point. You can't change an object's boiling point. You can't make something boil at a lower point or a higher point. Okay? You can change temperature, yes. But that's not what she changed. That's not what we're observing. First of all, what are we observing? If I had to plot this on a graph, what two things am I plotting on the graph?
Molecular mass and boiling point,
Isn't it compound and boiling point?
You can maybe say molecular mass and boiling point, so either this one or that one. I don't think that's necessarily what she's comparing. I think she's simply comparing the compound with the boiling point. Okay? Now you can't change you can't make something boil at a different temperature. Okay? So I would say the independent variable is then either molecular mass or the compound. Okay, so it's not necessarily a number that you're plotting on the graph. Okay? So either that or molecular mass. Okay, what is the dependent variable? That's the boiling point. The boiling point depends on the thing that you changed. If you change the thing in the container that you're boiling, then the boiling point is going to change. You understand? But you can't change the boiling point of the substance itself. So the dependent variable is boiling point. Explain why there is an increase in the boiling point from ethane to chloroethane. Refer to molecular structure, intermolecular forces, and energy.
The molecular structure of chloroethane is larger than that of ethane.
Good. That's good. First of all, the molecular structure is based on the molecular mass. So in other words, the molecule is bigger to begin with. What will that increase?
So
What type of forces? Okay. So in other words, chloroethane will have more induced dipole forces due to the larger structure. That's the one aspect of it. What's also different between ethane and chloroethane?
Isn't it the lower part?
Yes. Chloro, what type of forces exist when we put chlorine in as a molecule?
What do you call them? Because chloro
Chlorine.
is this one. It's hydrogen bonds.
No.
No.
Hydrogen bond is only when hydrogen bonds to a high electronegative.
Chloroethane. What is it again?
There's three options, guys. It's either induced, which we already said it is because chlorine is bigger, or it's dipole-dipole, or it's hydrogen bonds.
Dipole-dipole.
Why is it dipole-dipole?
Because the electronegativity of
Chlorine
yes,
is high.
high.
Yes. chlorine has a high electronegativity. So and so not just is it a high electronegativity, but it also is a large molecule. So there's two types of forces working here. So the intermolecular forces, there's increased, so chloroethane has an increased induced dipole forces due to the larger structure. It also has dipole forces due to the large electronegativity of chlorine, and then those together causes the intermolecular forces to be stronger. And now we must talk about energy. So what did they want us to say about energy?
Maybe the kinetic energy.
I don't understand. This is so simple. I don't know. I'm sorry, guys. I don't mean to. But it's all about the kinetic energy. Like, boiling point is about breaking free from the intermolecular forces. How do I break free? By getting more energy. So more energy is needed for chloroethane's molecules to break from the intermolecular forces. Does that not make sense? Like, is it?
That makes sense.
Okay, it's not Friday, it's not afternoon yet, so I don't know what else can be wrong. Okay. On comparing ethanol and ethanoic acid, state the trend observed between the boiling points of ethanol and ethanoic acid. There we have ethanol and ethanoic acid.
It's increasing.
Okay. So what do you see in the trend observed?
It's what I don't know how to put it, but it's okay. Let me use the intermolecular forces.
No, they just ask you for the trend. So then just how did they compare?
It increases as it goes from ethane to ethanoic acid.
So it's ethanol and ethanoic acid.
Yes.
Yeah, so that's it. Ethanoic acid has a higher boiling point so that's the trend. Okay? Explain that trend. Now we come to that. What would make any difference? What's the difference between them? Why is there a difference? What's the main thing? The easiest answer? The forces, that's it. Okay, so we know that the one has stronger forces than the other. We just now have to go and prove it. That's it. We just need to show which one has the strongest forces. Now we know which one has the strongest forces. Which one?
Ethanoic acid.
So what's the difference between ethanoic acid and ethanol? So we need to draw. Ethanol would have 2 carbons connected to a hydroxyl. And then the rest is hydrogens. Ethanoic acid will have 2 carbons connected to that with a double bonded oxygen.
So we have, in both cases, hydrogen bonds, and we also have in the carboxylic acid another force.
Which force is that? Olivia?
I'm sorry.
This no.
Dipole.
Dipole. These only got to do if they have different, but it could have worked as well, because instead of having a hydrogen, I now have an oxygen, which is also larger than hydrogen to begin with. So you could have maybe gotten away with induced as well, because it does have a larger molecule as well. But the biggest difference there is the fact that we have a high electronegative compound in there. And then it is dipole. Okay, and now we must just refer to energy needed. So, more energy is needed to break free from the intermolecular forces in ethanoic acid. Okay. Will the ester methyl methanoate have a boiling point higher than or lower than ethanoic acid? State only higher than or lower than. So let's go draw it quickly. Methyl methanoate looks like this. So methyl let's first just draw the ester structure. It's the ester structure. Methyl means on the oxygen there's only one like that, and on the other one there's only one here. CH3. No, not CH3. Just one H. Okay. Oh, guys, I'm so excited because you're going to get it right. Okay. Let's just reason it out. What is the simple answer? What are we looking at? Forces. What's the difference between the... We looked at the forces here. Here was dipole. And there was also hydrogen bonds because of this dude there. Hydrogen bonds. Okay. What's the difference between these two?
We have dipole forces in the ester.
Yeah. Two dipole forces. Thank you. Roughly the same size molecule, so there's not really induced dipole differences.
The answer is.
I'm waiting. Very anxious. Don't be. You're going to get it right. Because you know this. You must just think. Makani, what do you think? Not what do you guess, what do you think?
I think that one is the highest boiling point.
You think?
Yeah.
This one?
Not that one.
This one?
Just below. Yes.
Why?
Isn't it because it has two dipole forces? So it makes it a...
Well, which is stronger? Dipole, dipole, or... Because what's the difference? This one has two dipole forces, and that one has a dipole and hydrogen bond. So the question is, which is stronger? Dipole or hydrogen bonds?
Hydrogen bonds.
Hydrogen bonds are stronger. Because hydrogen bonds are oxygen pulling on hydrogen. Dipole is oxygen pulling on carbon. Carbon pulls roughly the same as oxygen, while oxygen pulls very hard on hydrogen, making it very negative. So which one is better?
The top one.
This one will have a higher boiling point.
Because you said it's better to have a lot of weak people on your team.
Yeah, let's think of that. Okay, so the strongest guy is hydrogen. Okay? And so I've got one strong guy here. I've got the normal guys are dipole, and then the weak guys are induced. Okay, so induced means I am adding another carbon, or my molecule is increasing a little bit. It's like adding just another weak guy. But if I have a hydrogen bond, and on the other side I've got a hydrogen and a weak guy, then obviously this side's going to win, because I've got one extra carbon. Okay. The question might maybe be, how many of these must I have to be as strong as those? You understand? But they won't ask it like that. Do you understand what I mean? You will always be able to draw your strong men on that side and know, like in this case, we've got a normal guy and a strong guy against two normal guys. Who's going to win? Normal guy and the strong guy. Yes. Okay. Now they ask you to explain your answer. That's the answer. Okay. The hydrogen bonds. Not stronger and weak guy. Okay, sorry. The hydrogen bonds are stronger. The hydrogen bonds in the ethanoic acid is stronger than the dipole bond in the ester. Okay. Okay, one more question and then we're done. Consider the 7 organic compounds represented by A to G. Write down the letters that represent the following. Okay, a compound with a general formula of. Okay. So this one, the aldehydes. Okay, aldehyde will have C. Let's say 2, just so that we can do the difference between aldehydes and ketones. So this one will be C2, H, 1, 2, 3, 4, O.
Mm-hmm.
Yeah.
Okay. And then you get your ketones, which should be the same. Because the only difference between a ketone is that your double bond is not on the end, it's in the middle. And it wouldn't change the difference. It's just a different carbon that has the double bond. So this one will either be a ketone or an aldehyde. So that's what I'm going to look for. Where do you see it?
E.
E. There you go.
No, D is off. I just left it.
Yeah, DS2, that's an ester name.
Please go up, sir. Okay. And then C.
Oh, did they ask for more than one?
Yes.
Compound or compounds? That's good. Yeah, C. Sorry, there you. I didn't see that. So in other words, there's 2, 4, 5, 8. 1, 2, 3, 4. Yeah, that also fits this one. Okay, so those two. So this one and that one. A structural isomer of pentanoic acid. So a structural isomer means they've got a similar structure.
No. Same molecular formula but different structure.
Yeah, molecular form, but this is a structural isomer. An isomer has the same molecular. So pentanoic acid has pentanoic is C C C C C O H. Double bond there. Okay, so that's pentanoic acid.
Yeah, D.
D.
Yes. I think.
Yeah, there we go. Now, is it?
You always
Because that
say
carbon, that oxygen is there, that carbon bonds there.
But there's no OH.
There is.
D.
Yes.
No, D is an ester.
H3.
What is the OH?
There's a double
But
bond.
then still, so they said thingy.
Okay, wait, let's just go up and you'll see the other possibilities.
Okay,
That's
we'll look
18.
now. I just want to count this. This is 3, 2, 4, 6
Oh, I see what you mean.
plus
Yeah, I
4
see what you mean.
is 10 and 2 oxygens. But I think that's fine. 2, 4, 6, 7, 8. We only have 8. 2, 4, 6, 8, 10. Yeah, no, it will work. D will work. Okay.
But I got it wrong. It's common.
And then there's not anything else that is paint in here anyway. Well, this one maybe. 1,
Nope.
2, 3, 4, 5, 6. No. Okay. Mono. What? Okay. So a monohydric alcohol. What is a monohydric alcohol?
One hydric alcohol.
I would Same. This one has only one alcohol.
Is it hydrate?
What's hydric?
I don't know.
Well, we don't either. So I think it's fine. It just needs an OH. That one has an OH. This one has too many OHs. Mono just means one. Monohydric alcohol. Okay. An aldehyde. Okay. Aldehyde would be when it has a CHO. That's what we're looking for. That one, huh? I think so too. There's the CHO at the end. So I think an aldehyde will always end on CHO. We'll have Coo's will be our butanoic acids, CHO will be our aldehydes. Okay, write down the UPAC name for C. C, 1, 2, 3, 4. 1, 2, 3, 4. Which would be?
Ethanol.
Butanol. Well done, butanol. Okay, for C, F and G. F would be 1, 2, finding the longest chain, 1, 2, 3, 4, 5. That would be pen. What should the N be?
Penta 2. No, penta 1 and 2.
1, 2, 3, 4, 5.
Yes, 1,5. A diol.
Diol, well
And
done.
then in front you need to put in 3-methyl.
3-methyl penta 1,5 diol. G.
Chloropropanol, I think.
1, 2, 3.
No, dichloro. Wait. Yes, dichloropropanol.
I don't know which side you'll number. I'm sure you'll number the alcohol at the back. But I don't think that will be necessary. Anyway, chloro will be on the second in anyway. So this one will be 2.
Isn't it?
Carbon 2.
Is.
Dichloropropanol. Yeah, that looks fine. Okay, that was G. Draw a structural formula for compound A, ethanoic acid. So, if you know it's ethanoic acid, just start with that. And then, so all you need to know, and there's not a many, there's only 6 of them that we need to know. And then ethanoic acid just has that, 2 carbons in it. Structural formula. Alkenes can be made into polymers. We haven't done that. I won't do that now. I think that's it. Right. Thanks, guys.